So I'm Doug Simon. I'll be speaking today about a project that was introduced last year and has come a fair distance since then. Graal is the name of the project, and it's all about, as we say, a quest for the JVM to leverage its own J. Skip through this one. So this is kind of a view of the JVM in terms of the people interacting with it. On one side, we've got the VM engineers or mechanics who develop and tune and work on this powerful engine underneath the hood. And on the other side, we've got the Java programmers who get to drive this sleek and well-tuned high-performance machine to solve all manner of problems. The mechanics have been doing fine with their set of tools, but they're quite distinct tools from what the Java programmers have been using. So the thing is, there's only a finite set of resources to work on and tweak and optimize the VM, and only a finite set of use cases for which the tweaking and optimizing is done. And as the popularity and performance of the VM becomes better and more widespread, the usage becomes more widespread, and different patterns are fed to the VM, which start to hit these corner cases that maybe a bit of tweaking and optimization hasn't been thought of yet for. And so, we can get expected optimizations to misfire. Some inlining may not happen, even though you've been told, write your code this way, and it should just, solve it for you. Maybe boxing isn't, or the optimization of unboxing isn't getting you where you want to be. And so the quest we're after here is to sort of take this set of tools and productivity suite that the programmers have had for a while, and see if we can sort of apply those down in the engine room and see if we get any further value out of here. And also, in some sense, empower drivers to be the mechanics. And so, this is how you can solve that problem of, I get to see why my inlining isn't doing what it's meant to be doing, or what I thought it should be doing. And actually, I have the tools now to tweak it. You've got other use cases that can be imagined. Maybe I want to run some analysis code over the bytecode, or Java programs, or whatever programs have been fed to the VM. Is there some way I can get at this wealth of functionality in the VM with the tools and languages I'm familiar with to solve that problem? And there's always extra use cases that we can't foresee that a VM may actually have all the necessary pieces to solve. Okay, so this is the approach we're taking. There's this bunch of sort of black box functionality in the VM, and we want to expose pieces of it via sets of Java APIs. And these are sort of the big pieces we have here. We've got this underneath, or at the bottom here, we've got something called the Meta API, and this can be thought of as sort of a richer and lazier introspection of the Java metadata, something above and beyond reflection. You can get a hold of the bytecodes, the profile information of the bytecodes. And then building on that, we've got this code API, and this allows you to generate code and install it in the VM. I mean, you get the sense, and you'll see this later, this is coming from our starting point of wanting to write a compiler in Java for the VM, and these are the pieces we need, but we've come to realize maybe these are useful pieces in and of themselves for other tasks. Yeah, so this code API, you can install and even execute code in the VM, apart from giving it bytecode. And this is great, we found, for black box testing, the compiler we've written. And lastly, if you're going to go down the route of writing the compiler or generating code, you probably want to hook into the VM's compilation request queue. And maybe even replace the existing one. You want to be the compiler for the VM. And then on the right side, we've got this interpreter API, which is sort of a building block for something you'll hear about in more detail tomorrow, but it allows you to directly execute a method on the VM. Not necessarily the bytecode of the method, but this is possibly in a different format. You get to play the role of the interpreter. And then to actually create instances of the objects exposed by these APIs, we need this Graal.api is sort of our service provider interface. This is where the VM-specific bindings can hand out your meta objects and your code objects and your interpreter objects, or take the callbacks that you express through these APIs. So the advantage of sort of doing things this way is that, or some of the advantages, apart from what we see as the Java development environment advantages, is actually VM development time can be greatly reduced. As we've been writing and developing our Graal compiler, we sort of Control-S, save in Eclipse, and start the VM. There's no need to do the whole make process of Hotspot. That's can be on the order of 2 minutes or so. Whereas this is the class files, the VM. We're not editing any C++ code in the normal case, and so this all just gets loaded into the VM and you're up and running. So in this picture, or in the picture of this instance that we're using day to day, the JVM is written in C++. That's why it's called out in a different color, but that's not necessarily the case. Some of us have a history working in another VM, Maxine, which is more of a pure Java implementation of a VM. Okay, so as I've sort of hinted quite a bit now, where did we come with these? Where did these APIs come from? And it's all derived from our initial focus on let's write a dynamic compiler for the VM in Java, and that's the Graal compiler. Now along this process, we've the APIs we have are derived from the requirements we had for this compiler. It sort of demonstrates immediate use cases and boundaries between the VM functionality you can express or expose in Java and the stuff underneath. We actually have a historic binding of these APIs to the two Hotspot and this other VM I mentioned. So we've sort of shown that we've achieved some degree of VM independence there. The interpreter APIs developed in the context of a project to explore new ways for executing other languages on the VM, something you'll hear more about tomorrow. But to show this proof of concept works, we've written a bytecode interpreter, sits on top of this API, and can actually play the role of, it doesn't replace at the moment due to the obvious bootstrapping issues, but it can complement the template interpreter in Hotspot. And then building on top of that, as I mentioned before, we're not interested in just being able to interpret the bytecode method. We want this some arbitrary format associated with the method to be executable. And so you can think about an AST form of Java methods, and we have something like that and an interpreter for it. And so this is now a conjecture of other tools you might want to write on top of such APIs. You might want to analyze the profiles gathered by the VM while executing bytecode, much like the compiler does, but maybe you have another use case for this data. Okay, so a lot of this presentation is going to be about sort of architecture and APIs, but I also want to reassure you we do care a lot about performance. This is where we started from. We want to get as close to, if not surpass, the server compiler as possible. And we've been tracking our performance quite rigorously. Every pushback we do, we have a benchmark run, and you can see this progression here, where a higher bar is better. We started in November, sort of once we had the system running to the point we could run the benchmarks. We were slightly below the client compiler. Things didn't change so much in December as we worked on fleshing out the architecture and the features of the compiler. And then we started gaining momentum here in February, where we surpassed the client compiler. This is mainly due to a lot of tweaking of inlining or improvement of inlining heuristics. A few more local optimizations got us to our roughly current point of 26% better than where we were, and not quite midway between client and server, but we're fairly confident. We can go a long way from here. We've got a lot of performance optimizations, improvements in the pipeline. We don't inline the fast path for synchronization. The scheduling at the back end is fairly naive. We don't do array bounds, check elimination, a lot of the standard optimizations. And we also don't do a lot of the intrinsifications the other compilers in Hotspot do. We also track our performance on a bunch of other benchmarks. This is JVM 2008, but due to discussions with other groups, especially the Scala group at Lausanne EPFL, we're tracking our performance on the Scala Decapo benchmarks, Spec JBB, Decapo, a bunch of these things to make sure we don't just get one benchmark-driven profile curve. Okay, so, as I mentioned, we're doing this on top of Hotspot, and I don't think I have to advertise too widely why this is not such a bad choice. It's just a whole raft of features that we get for free, or we don't have to reinvent by going with Hotspot. We can sort of focus on the subsystems, such as the compiler, that are of immediate interest to us while leveraging this huge investment. Also, being positioned where we are inside Oracle, we have access to this wonderful QA resource that the product VM goes through, which you only get if you're working on the same code base. And same with the robustness of the VM. So it's all about. So I'm going to dive a bit deeper in the next few slides into the APIs we've had and how are they used and how they can be used. But this is sort of a slight commercial break for how we'd like to open up the system and actually encourage participation or collaboration. We've made this as easy as we can. First of all, creating this project under the Open JDK umbrella gives us the infrastructure we need to make the access easy. We've written our own little Python-based tool. We call it the MX tool. And this really simplifies all kinds of interactions with the code base. It's sort of a mixture between the Maven module dependency tool and something like the HG, the Mercurial command line interface. So we can build the system, execute pieces of the system all very simply here. Here's the recipe. You can download it, build it, and start to browse it. We have the same tool I just mentioned can build up or generate Eclipse and NetBeans, IDE configurations, and Bean Java. These are the best tools to browse and interact with the code. And then we've got a mailing list which we encourage those interested to join. Okay, so let's dive down a bit into the Meta API I mentioned. And this is kind of a trivial demo, but it shows you this use of this extended reflection. And this is a complete standalone program where we go and get a handle on to Graal, the provider of the Graal APIs. This is what we call the Growl Runtime here. Or through this Graal.getRuntime, we get access to some meta level provider. And what we want to see here is just in a execution of the VM without any program, just run the VM and wait for it to give you the usage message. How often does the value of method of the string class get called, and what does it profile? What does the interpreter? What profiling information does the interpreter gather on this? There's this is obviously data that's consumed by the compiler itself, but we've sort of been inspired by some of the technology coming from other VMs such as JRocket, where they also realized they were doing a lot of data gathering and thought maybe we can expose this to interesting tools. And so you've got this mission control tool that sort of really makes use of a lot of the VM profiling that's been done. And we also get to see here maybe what's interesting for the compiler highlighted in black. Every time this, first of all, it's amazing how often value of is called on string on the empty command, Java command line, not even running hello world. Or, this is a very simple, some hello world-like program where we don't do much intrinsic usage of value of here. And then we also see that, a good over 99% of the calls to that actually take a string as the receiver type. And so you can quite quickly see how a compiler might do some sort of guarded inlining here, speculating on string being the most common type coming through. And once again, you can write these sort of little experiments very quickly without having to modify one line of the VM code or do any VM rebuilding. Okay, So the next API I called out earlier was what we call the code API. And this is primarily intended for writing a compiler in Java to execute on the VM. This compiler produces something called a compilation result, and that gets installed through the installation capabilities of the API. And what I'm showing here is the way we use this to write a very simple black box testing framework for our compiler. So what we can do is take a method, feed it to our compiler, have that install the code that it generated, and then directly execute it. At the same time, we can execute the same method through standard Java reflection, and we just get to compare the results and Bob's your uncle, as we might say down under. You've got the result you hope you get. There's a simplified framework here. Obviously, you're going to have to take care of exception handling, but the same mechanisms apply. There's nothing more intrinsic. There's no extra API needed to write the complete system. And once again, the ability to install arbitrary machine code for methods will be demonstrated. The powerfulness of this will be demonstrated more tomorrow. And so the next layer of the VM exposed in Java, these are nice APIs you can target, but maybe you want to go a bit deeper. And this is where the compiler we've been writing is solving both the performance or shooting for a certain performance goal, but you also want to make the compiler as extensible as possible for those who may want to tweak what a compiler does for their application. And so this is sort of the rough mission statement of what we're after with this compiler. I'm not going to read it out here, but the bits bolded out sort of what I'll go over in more detail in the subsequent slides. Our performance goals are on track, as I showed in the benchmark numbers. And now, I want to show you the extensibility features of the architecture. Before doing that, I'll repeat some of the high-level design points about the compiler that were mentioned last year. It uses a SSA-like, or an SSA intermediate representation, sort of close to the sea of nodes IR used by the server compiler. Has a linear scan register allocator at the back end. That part's subject to change. But the high-level IR is sort of where the focus is and where the extensibility is. As I mentioned, it's been historically integrated into two VMs. So we think we've got the VM and runtime, the compiler and runtime abstraction fairly well correct. Okay, so don't squint. You're not meant to really see the details of that graph, but this is just trying to highlight the modularity of the compiler. These are all the source code projects that make up the compiler. And we believe, we'd like this to be twice as much. The modularity really does help you understand the separation of concerns. And once again, as with a lot of the slides, I'll show you sort of the little usage of the tool we have that can produce these sort of artifacts. And as I said, the tool generates the IDE configurations as well as these kind of outputs. It also automates a output to a graph visualization tool. So there's a lot of benefit you get from sort of this declarative approach to describing the projects or the modules in a project. Okay, so what does an extensible node look like in our compiler? What we have here is a specialized node which won't come from standard Java programs, standard Java bytecode. It has the semantics of something like a field store, but it doesn't, it's not a de-optimization point. There's no side effect here that you can't sort of rewind back behind. It's also, we ignore the write barrier semantics of required by the Java memory model. So this is something you might start to imagine we use at a lower level of the VM to express or to lower down something like a field store with all the correct semantics. It's also used in the intrinsification of system.arrayCopy. And it's kind of interesting that we're using Java code to do this intrinsification. Normally intrinsification is done by hand weaving some kind of compiler IR. And you'll hear more later on how we do that with Java source code. A couple of things to note here. The use of annotations. So these input annotations, they declare the edges in the graph. And that's it. There's no other need to say where the edges in the graph are. The metadata that reads these annotations allows for sort of fast iteration over the fields of nodes. You don't see a visitor pattern here. You know, visit my inputs. The metadata API that or facility that is based on these inputs or these annotations uses it does low-level use of unsafe to get the offsets of these fields and can give you sort of array-like access over inputs of nodes. It's quite important when writing transformations. Quite often you don't really care about what position the input is. You just want to look at all the inputs of a node. The unannotated nodes, fields, not particularly in this node, but for what we call floating nodes. This is a fixed node. In the graph, it cannot move around. But there's this distinction we have between fixed nodes and floating nodes, where floating nodes are those things that can be sort of global value numbered and commoned out together. And quite often when you want to do that, you need some sort of input to the key used to do the GVN operation. And once again, we can use a reflection here. The metadata class says anything that's not annotated with input or successor forms part of the key of a node. And so no need to write any explicit code to in your new node that you're adding to the system to get global value numbering capabilities. So I've hinted here that we have this, this method here actually shows how you tell the compiler to go from this node to lower level nodes. All compilers have to do lowering. You start with this very high level nodes or even bytecode, you're going to end up with machine code. And what you're doing is continually replacing these higher level, coarser grained operations with lower level expression of those semantics. At some point, incorporating the semantics specific to your runtime. So here, a store node has to be reduced at some point to this lower level write node. And so you can write that here. Once again, we didn't need to go and modify the compiler. The implementer or the provider of this new node encapsulates everything the compiler needs to know about the new node and how to get it finally down to machine code. Okay, so here's an example of the visualization tool driven by these annotations. This is the zoom view of the tool. We've zoomed on this object node, and the green line, the blue lines here denote the inputs to the node. You hover over one of those lines, you get to see the field name corresponding to that node. This is all extracted from those annotations, and the red lines are the control flow edges of the graph. There's a little recipe down there how to start the visualization tool, and on the website is an example of the command line switches you need to generate output for whatever methods you want to visualize. We also show the properties of a node. These are the unannotated fields of a node, all extracted via reflection. No need to write anything in your node to do with visualization. And this visualizes as is denoted by this command line here, part of the tool base, code base. So carrying on with this node, what I want to show here is something we call node intrinsics. And this is sort of a building block of how we express lowering with Java source code, something we call snippets. Quite often, what we want to do here, you see this little snippet of code below where we have this call to direct object store node dot store object. When that code is compiled by our compiler, normally, or by any compiler, that is going to be represented as a call. However, this store object method, you can see in its declaration, is annotated with this thing, node intrinsic. What our compiler does is says, oh, you know, I see a call to a node intrinsic. What I expect is therefore to be a constructor of that node, the associated node class, that has exactly the same signature of this node intrinsic method. Same in terms of shape and constantness or not constantness of the parameters. So we can see here the constructor takes 3 arguments of type value node. They're sort of the non-constant inputs. These are true inputs to this node, and a primitive type, primitive value displacement. And this has to be, you know, when you're going to call a constructor, there really needs to be an int value there. And so in the node intrinsic method, you see this annotation saying, here is my constant node, my constant argument. And what the compiler does is, you can see here, when it sees this call, it replaces that with a using reflection. It goes and instantiates, calls this constructor using the IR nodes that are in the graph that's been compiled corresponding to the inputs of the node itself. And you may notice here another use of annotations. So I said this displacement value needs to be constant. And actually you do see here, it's given a different name. Actually, it's a bit of a bug in the slides here, but this offset argument going in doesn't look very compile time constant. It's a result of calling something. But if you look at what it's calling, that thing is annotated with another annotation we use, fold. This tells the compiler, when you see a call to this, don't go and compile it. Just execute it via reflection. We're running on a Java VM. We can go and reflectively execute things. Take the result of that, and now you've got a compile time constant. Plug it in. And this sort of all folds together nicely. Okay, so that's a specific node. So how does some of this magic happen as nodes are created? Here we have sort of the core initialization code for a node. This is called from the constructor of the node base class. You see here that each node has a metadata class. And that's what's used to sort of gather up the offsets of all the annotated fields. And that's where we get the fast iteration through those annotated fields. We can also support fields that are not single values but lists of values. If you think about, so de-optimization requires the frame state at certain nodes to be known, and frame states are variable length data structures. And so you have this variable length set of inputs to certain nodes. These can also be annotated with @input, and we recognize those lists, and we just get the offsets of these lists inside these nodes. So we still get the fast iteration. We also see down the bottom here in the example from the graph.java source code, source file, the ability to iterate over the nodes of a specific type in a graph. And this really is linear time iteration over nodes of that type, where over the number of nodes of that type in the graph. And this allows you to write certain transformations that perform actually fairly fast. There's no need to scan the whole graph. Okay, next slide. So another thing we've made extensible in the compiler is the sort of the way graph transformations are composed. Our compiler is actually more of a compiler toolkit. We have this graph library, bunch of nodes. We have an abstraction for expressing graph transformations, and we have a mechanism by which those transformations can be composed, what we call a phase plan. And the compiler that sort of actually executes in the VM is really just one instantiation of a phase plan, which can either be completely replaced or, as I show in this example, customized. And so I'm using this here to white box test some of the compiler. As I mentioned lowering. We need to, at some point, lower invocations that haven't been inlined. At some point, you really will have calls in your graph. So there's part of the compiler that has to do that transformation. However, writing a test case is actually pretty tricky in a compiler, in a VM like Hotspot, where it's the profile information, a whole bunch of sort of runtime or environmental context can decide whether a certain method is inlined or not. And so you can spend a whole lot of time trying to craft your test input such that you know this won't be inlined. And you may get it right, on that day, and then someone tweaks the inlining heuristics and, now my test doesn't actually test how I lower an invocation at all. It's just when it got inlined. So this shows another way to solve that problem with the extensible phase plan customization I mentioned. Here we have this testing framework that gives test classes an ability to modify the phase plan before it gets fed to the compiler proper. And all we do here is we say, well, remove the inlining phase. Do everything else you planned on doing, but don't inline. And now I know that I'm guaranteed to test the part of the compiler that will actually not inline this, this call to private method here. A small private method is almost always inlined by a compiler, especially if it's on a hot path. So we get to really customize here, and you can hopefully imagine other uses of being able to customize your phase plan. You might pull out this inlining phase and add your own custom inlining phase that looks for your application-specific methods. Now we're looking at the sort of a further example of white box testing the compiler. Another thing that's hard to test are compilation paths or compiler code paths that deal with profile information. Profile can come in all sorts of shapes, for a given bytecode, it can have a profile that will drive the compiler this way, that way, or not at all. And you really want to test all of those code paths. This is even harder than trying to prevent a method being inlined or not. You really want to say, here is the profile for this specific profile-driven bytecode instruction. And so what we can do here is actually go and modify the graph before it's reduced to machine code by the compiler. And here we see an example of this ability to iterate over or create a view on the graph. We just want to see the checkcast nodes. And we want to look at the first one. So we know in our test program there's only going to be one. So we pull this guy out, we get his profile information, and we replace it. We replace the whole node with a test-specified profile, as I show here, the set per test. We can, for different test cases, we have mechanisms saying, here's the profile I want to use. And so we just write a profile that tests each of the compiler code paths. So you're really getting at the internals of the program being fed to the compiler, quite simply. Okay, now I'll go a bit more in detail of how we do this Java source code base lowering. What we have here is some source code for lowering a checkcast. This is expressing one part of the semantics of how Hotspot does lowering of checkcast instructions. If you know you're a final type, a leaf instruction, your checkcast should be a little more than just an equals comparison against the given type. Here, for example, string. And so we can express this as Java code. Java code, we can feed to our compiler and build up a little subgraph. And this little subgraph, we can sort of cache on the side and say, when we, at a real compile time, we hit a checkcast with this pattern of a final leaf class, take out the checkcast node and just inline this pre-processed and pre-prepared subgraph. To do this, we need to have support for incremental inlining, which we do. We have support for incremental graph-based inlining. And once again, you can see the use of node intrinsics and compile time folding here to make this possible. the only other way to do this is to hand weave a bunch of C1 or C2 or whatever your compiler's internal IR. So this is how we do lowering with snippets, and here it is in sort of visual form. The graph on the left is the result, the graph that came out of feeding the previous code into the compiler. As you can see here, we have a if I go back, you'll see that once again we annotate the arguments to the snippet. There's 2 variable inputs and 1 constant input. What we do is we say, okay, when it's a constant input, that means this graph can be specialized for different values of that constant. And we do this lazily. So when you go to compiler check cast, we had this constant input saying, do I need to do a null check? Because it may be that the node you're about to replace, the check cast tells you, well, I know due to previous analysis, the null can never actually show up here. So we can remove that code path altogether. And so what we do is we specialize this graph with that parameter being null, and that becomes sort of a hash into a hash key into a cache of specialized snippets. And so here on the right is the graph after specializing the graph with a constant binding of check null true. And yes, it's a smaller graph which will take less time to inline and do the lowering. And then when we actually instantiate this while we're lowering a given checkcast node, all we have to do is take the object input and the exact hub input of the checkcast node and bind it to these 2 parameters here and do a normal inlining. And this use of incremental inlining is not only used for the snippet lowering, but also for tail duplication and also escape analysis. We do escape analysis at the IR level, not the bytecode level, which means you can do sort of a partial escape analysis, application partial escape analysis. So I think that's where I'll stop the deep dive. But the major point here is that we've sort of really looked at trying to open up the VM with these APIs, with the use cases we have in mind that we're using today. We'd love to hear of other use cases you may have in mind for such an opening up of the VM or programmability in Java. And at the same time, we're focusing just as much on performance as extensibility. Like I said, we've got a lot of ideas of how to push that performance further. And that's where we're at today. Is any project of this scope has a lot of people involved in it. We've got sort of a core team at Oracle Labs, a bunch of really sharp students over at Linz University in Austria, and we've had a lot of fruitful discussions with people both in this room and at Oracle Labs. We couldn't have gotten this far this quickly without them. And so with that, I'll open up for Q&A, and here's the recipe if you want to get involved.